Greetings, math friends. When I was an undergraduate taking early calculus courses, there were some things that I didn't quite realize what they were or how they worked. And I think this becomes tricky for us, especially when we're in a test situation and we expect things to be one way and we see something that's slightly different. And we're already in that test mindset where we may be stressed, slightly panicked, and then we see something unexpected and we are stuck. I want to look at a few questions here. One of them is focus of what I'm talking about here. A problem that I encountered when I was in my early undergraduate class that was kind of a trick question. I got it wrong. Other people in the class got it wrong. We didn't understand a concept that we probably should have, but it just didn't register for us. It probably wasn't made as explicit as it could have been in the class session, and then when we saw it on a test, we didn't process that, and we didn't process it properly. Now, I don't think everybody in the class got it wrong, but there were a few of us that I believe did. So let's look at some problems. The first one we have up here is we're going to integrate sine x. You've probably memorized at least a few of the things dealing with trig. The derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared. You probably have at least that as base information to work with. This is a little tricky because you can't just switch this to cosine. Because remember, as I just said, the derivative of cosine is negative sine. This is positive. So how do we do that? We need an adjustment factor. So we have to come in here. We really want a negative sign, but we can't just add a negative here without some justification. And the justification is that we can take two negatives, multiply them together, and make a positive. So we're going to put an adjustment factor of -1 outside here. That if it would have been in here, we split this into two -1s. We pass one through the integrand. We leave the other one in here, and then we can come up with our antiderivative. And then we'll evaluate from 0 to pi halves. And we can work that out from here. Hopefully, again, you have some understanding of the cosine of 0 and the cosine of pi halves. Maybe even go back to your unit circle. We're looking at this point up here and this point down here. Our cosine values are x's. And then our sine values are y's. So when we're at this point here, we are at the x is 1, and then the y value is 0. So we're at the point 1, 0, when the angle here is 0 degrees, and this is what we're talking about here, the angle. So when the angle is 0 degrees, our x value is 1. So this is going to, cosine of 0 is going to give us 1. Up here, we have that our x value is 0, and our y value is 1. So when the angle is pi halves, our x value is 0. So looking at this, expanding this out, we have cosine of pi halves minus cosine of 0. That's going to give us 0 minus 1, giving us -1 as the value for this integration. But remember, we had the adjustment factor. So really this thing here, properly notated, we need to have some brackets around here, and we have the -1 on the outside. This calculation here, we also need that -1. This calculation here, we need that -1. And then this calculation here, we need that -1. -1 times -1 is +1, and that's going to be our final answer. So sign mistakes are typically common. seeing that we need the adjustment factor and also carrying that adjustment factor through the entire calculation is really important to get all the points for this problem. When some of us first saw this integration, we thought it was going to be pretty straightforward. Though we have a pi in here, we have a fairly quadratic look to it, so not really too much of a crazy challenge here. But some of us either didn't understand or didn't realize because of the pressure of the test that the differential over here had pi, not x here. So this is integrated in respect to pi. Pi is a variable, not a number. So that was an issue for us. That was an issue for me. I got this wrong because when I integrated this, I did this with respect to x. So I would have had something along those lines, which would have been incorrect. So now the exponent on pi is 1, so this will end up being pi squared. So we'll have this, and also we need the x squared in here. So that when we do the derivative of this term, we will get back to this term. And then very similarly here, we are going to have 5/2 x times pi squared plus 1/2 pi squared, and then we're going to evaluate that from 1 to 2, keeping in mind that pi is our variable. In here we're going to put 2 wherever we have a pi. So this is going to be 3/2 x squared times 4 because we're squaring 2 here, plus 5/2 x times 4 again here, plus 1/2 times 4 again here. And from that we're going to subtract 3/2 x squared 5/2 x minus 1/2. Okay, and then we're going to bring all those terms together. So we have, we're going to multiply this together. This will end up being 6x squared minus 3/2. 6x squared minus 3/2 x squared. Over here we're going to have 10x. And then we have minus 5/2 here. We're going to have 2 here minus 1/2. And then we'll clean that up. So when we simplify everything, we end up with 9/2 x squared plus 15/2 x plus 3/2. So that's the proper way that you would integrate this, because pi is our variable here. We're left with this polynomial with the x's still in it. For the last integration here, this may not seem like a challenge to many of you, but this form at times causes me confusion. I expect to see, or especially in the past, I expected to see where we have the integration of 1 over x times dx. And I don't think I always understood what the dx was doing. What was it? What does the symbol set mean? And how can it be used? Well, one of the things is, if this is a term that's being multiplied by the fraction, then we can multiply them together and simplify this integration to look like this. If we understand what this is really telling us, then the integration for this is, again, fairly straightforward. This is going to be the log of absolute value of x, and we're going to evaluate along the interval that we're given, the limits of our integration. So if you understand the differential notation and that this actually multiplies together and you can condense it like this, not necessarily a problem. But if you don't understand what you can do with this differential, this might end up being a problem for you. With this, there's nothing that needs substituted in here. We can just work from this position and go ahead and do this integration. So we're going to end up with the log of 2. Final answer. This problem has stuck with me for years. I think especially since it was in a test situation and not a normal lecture, it especially imprinted on my memory and my thinking to be very careful about what term you're integrating in respect to. We have multiple variables here, and we many times want to automatically think that pi is the irrational number, but it also is a variable, and this is a case where it was used as a variable, and that kind of threw me and maybe some of my classmates off. Again, with the pressure of the test, when you see several of these things that are integrated with respect to x, and we have x in here, maybe we're not actually paying attention to the differential. We're just kind of in the follow through of the programming, and we think, well, respect to x, we're going to do this respect to x, this respect to x, and then we just follow through, and we end up with an issue at that point. So I guess one of the things as an outcome to watch for is to understand what the differential is and what it does, and to be aware that this variable here is going to be something we need to watch for, because it's going to tell us what we are doing over here. Now, if you've done multivariable calculus, then an issue like this isn't really an issue, because you're used to selectively ignoring multiple variables. But for early calculus students, this is something that we need to be aware of, what the differential is and how it can operate, what it does, what it tells us, what it informs us about the calculation that we're trying to do. And I'm not sure that it's always gotten across to students in an impressionable way, or in a way that conveys the right information so that the student understands what it's doing for them and what it's informing them of. So maybe for those of us that teach calculus, we want to take that as a thought to carry into the classroom, that we want to make sure that students understand what this differential term is doing, and help the students understand what it tells them and what can be done with it. Cheerful Calculations.